No, the leads don't twist up. I'm sure you've seen it in the model, and you've seen it actually in the lab. It's a little bit difficult to get your head around why the leads don't twist up. It's a little bit difficult to actually work it out. I quite like this picture showing why it is that leads don't twist up. Imagine you have a dumbbell, a bit like people use for weights, yeah? But this has got a rubber handle. If you rotate that dumbbell, you can see that this will rotate the same as that. No problem there. Now keeping it rotating there, you just bend the handle, bend it over, and you will now have the two rotating like this, still with your handle in the center. And that is why the leads don't twist up. Here we've got both rotating, but what we could do is you could hold that one and just rotate this one around it. And there's your J-type CCC machine. That's why the leads don't twist up. And that just shows that you've got the previous picture. You can put one on the bottom as well, and again, the leads won't twist up. So there you've got your J-type machine. However, there's a penalty though. In order to not have the leads twist up on the J-type CCC machine, you are fixed to one rotation around the sun gear for one spin around its own axis. You're fixed to a 1-to-1 ratio. It spins and it rotates, yeah? And you're fixed to that ratio, meaning you get one mixing step and one settling step per spin around the sun gear. Is that the optimum? Could it be that you need more mixing steps, fewer mixing steps? So this is the reason why you might want to look at a non-synchronous CCC, or this is the reason why we did in the research. We thought perhaps there are some phase systems where you want lots and lots of mixing and then only settle it occasionally, or just a small amount of settling. Or it might be that you have a delicate phase system, like the aqueous two-phase systems, where you don't want to mix it too vigorously, but you want a very strong settling force. So being able to alter that ratio of mixing to settling is what the non-synchronous CCC is all about. It's taking away from that 1-to-1 ratio and making it so that you can alter the amount of spin to the amount of rotation. But you might say, there's a penalty. You need a rotating seal, much like the CPC machine has. No, you don't. If you design, and this has all been done by the engineers, here's your J-type machine. If you design your flying lead with this clever mechanism just here, then you can alter the amount of spin to the amount of rotation without this lead twisting up. Now, you might not quite be able to get your head around it, I can't, but trust me, it works. I've used this machine and I haven't seen the leads twisting up, so trust me, it works. The engineers will tell you how it works, but the leads don't twist up. This is the engineering diagram of the machine. You need two motors, because you now need a motor in order to spin the coil, and then you need another motor to rotate it, because they'll be going at different speeds. And here's your lead path for the first bobbin that's just here, and here's the lead path for the second bobbin, just there. And the machine itself looks like that. So what does it actually do? Well, going back to synchronous CCC, standard J-type CCC, you've seen this picture before. You've got your 1-to-1 ratio, you've got the sun gear, you've got the planetary gear, and when you plot the path that this point P takes as it goes round, you get the shape known as a cardioid, loop-the-loop, and then a big high G-force, and a loop-the-loop, high G-force. So you get one mixing step and one settling step for every rotation, for every turn of the coil. When you can alter the amount of mixing, the amount of settling that occurs, you can get all sorts of interesting patterns. Here is the one we had on the last slide. This is with the 1-to-1 ratio. So here is the ratio of bobbin to rotor speed. And you can see that on E, it's at 1. So when you've got a 1-to-1 ratio, you get the cardioid shape. Yeah? When you have a 0, you get it like this. And I think I'm right in saying that would be an I-type machine. Am I right? This will be an I-type machine, which will be a bit like taking a beaker and swirling it round like this. Yeah? If you have a ratio of, now let me get this right, C, 0.33, you can see you've got a little mixing and lots of settling. What you're getting there is you're getting the rotor rotating 3 times for every mixing cycle. Here with, what am I looking at? F. So F here, you're getting 3 mixings for, let's have a look. You're rotating it 2 times, 3 mixings for 3, no, the rotor rotates 2 times for every 3 mixing cycles on this particular one. And on this particular one just here, you can see it's a minus value. The rotor is rotating in the opposite direction to the spin of the machine. Well, what we did was we took all of those different ways of operating, all 6 of them, and we injected 3 compounds onto the machine to see the separation. The 3 compounds were caffeine, ferulic acid, and vanillin, and here are the 6 different ways of operating. And you can see, I don't know if you can see it from the there, but it might be visible in your book. Here is the different ratio of rotor to bobbin speed, and we measured the stationary phase retention. Now, the 1-to-1 ratio is this orange line just here, and you can see in this particular case you've got quite a good separation, but you get a 30% better separation with this one just here, which is a 0.67 ratio of the rotor to the bobbin. So by altering the ratio, you actually can improve the resolution of your components by 30%. By the way, this arrow is the D equals 0 point, or KD equals 0, which is the solvent front, which will vary according to the stationary phase retention. And this line here is the distribution ratio equals 1 point, which of course is your column volume, so it's fixed for all the machines. So the interesting thing with this machine is that by being able to alter the amount of mixing and settling, you could probably, you will be able to fine-tune your separation to your particular solvent system. You can well imagine that some solvent systems will require a vigorous mixing, but only a little settling. Others, much more gentle mixing and a vigorous settling, a very strong settling. But you could optimize your conditions and get perfect separation by having a non-synchronous machine, which you could then tune to the having the right degrees for your particular solvent system. So the next work on the non-synchronous is, of course, looking at aqueous 2-phase systems. Now, my final mode of operation, special mode of operation, is called dual flow continuous extraction CCC. It's a bit of a mouthful, but basically what we're talking about here is continuous processing. You want to have improved throughput at manufacturing scale, and this is with continuous processing, so it's almost true countercurrent chromatography. So far, we've talked about countercurrent chromatography, where you have a stationary phase and a mobile phase. Now, this is the countercurrent chromatography coil. You've just got to imagine that this is coiled up, it's spinning, there's waves of mixing and settling going on and so on. It's just diagrammatic of the CCC coil. But here it is in normal phase operation, where I've got a stationary lower phase, a mobile upper phase. I pump the mobile phase in, it comes out here, and my components will elute in order of their distribution ratio. Distribution ratio of 0, 0.3, 0.8, coming out in order of distribution ratio. Of course, the alternative is that I could make the upper phase the stationary one and pump the lower phase in, and then in case I'll do it the other way around, and my components will elute in reverse order of distribution ratio. In this case here, I'll get D equals 10 coming out, D equals 1, D equals 2. That's assuming I keep the same ratio of for the same way of calculating the distribution ratio. The question you ask, why not introduce the sample in the middle? Why not actually just put it in the middle and flow both phases over each other? Then could you get out your low distribution ratio compounds at one end, and your high distribution ratio compounds out at the other end, and be continuously introducing your sample into the middle. That was the question that we had. Does it work? Well, it looks quite complicated to set up, but it's actually not that bad. Because most countercurrent chromatography machines, particularly the larger ones, will have two bobbins. And the leads don't twist up on a synchronous machine, remember? And so here's your first bobbin, here's your second bobbin. And since the leads don't twist up, you can just take the lead out of the machine, add your sample input, your injector, and then put the lead back into the machine for the second bobbin. The only complication that you have on the, when you're trying to operate it continuously is that at each end of the machine, you've got both an inlet and an outlet. You are pumping liquid in, and you're collecting the other liquid coming out. Now, in order to stop your liquid that's being pumped in just coming straight out of the outlet, you've got to put a tube within a tube in order to get the liquid started on its way down the coil, and then once it's started, it then just carries on going through the coil. So that's the only slight complication. Otherwise, it's actually a pretty simple machine to set up. So just to round off, I have talked quite a lot about CCC and the scale-up of CCC, and I hope I have shown you that it gets better as you make it bigger. It's a preparative technique. It's got a lot of advantages when you make it big, and there are, I think that it won't be very long before industry starts to realize that, and we start to see preparative CCC actually being used in pilot plants and in manufacturing plants. How big can it get? Well, we make jokes that they're not using the Millennium Wheel to very good effect at the moment, and what we like is a nice big coil put on it. You won't need to spin it very fast, remember? Big size, slow rotation, because you get the same G-force. So how big can it get? Well, we really don't know. Once again, I'd just like to acknowledge the team, because this has been a team effort. It's been work from all of these people. And then, once again, I'd just like to say thank you for your attention. And since I like penguins, I've got a picture of penguins, though. Thank you.